Hello there. Today we're going to construct an image similarity search system from scratch. Now, at the heart of this amazing system, we're going to implement a vector database using the robust and user-friendly open source platform known as Milvus. We'll harness the power of a Python-based script and then full-blown web app to add and explore images atop this vector database. Milvus is purpose-built to store vectors like embeddings for our semantic representation of images. As we move forward, we'll build out this diagram and shed more light on the architecture, but let's get started. As a convenient starting point, we could install Milvus via a Helm-based installation. Now, a quick trip to the Milvus GitHub repository will reveal that the Helm chart has moved. It's currently located at Zilliz's organization, a company powering Milvus's rise and one that offers a convenient managed Milvus experience. Let's navigate to the charts directory and we can start finessing the Milvus chart. Scroll a little and voila, we have the Helm installation commands that are our tickets to getting this Milvus instance up and running on our Kubernetes cluster. Talking about Kubernetes, we have two flavors to choose from, Autopilot and Standard. For some control and flexibility, let's opt for the Standard approach and bring up a 2-node cluster. This will cost us a measly 19 cents an hour. Once we have the cluster all geared up and humming, we'll switch gears and use the Cloud Shell for a Milvus installation. As we'll be running some code, it's prudent to also bring in an editor. Now comes the good stuff, the Milvus installation commands. Firstly, we'll add the Milvus Helm repository. Now that our Helm repo is up and ready, we can smoothly sail with the default installation. Remember, Helm offers us a sea of opportunities to tailor this installation with varied components and messaging systems, but we'll opt for a fuss-free experience with the default option values. A dash of personalization never hurts, so let's give this a catchy name other than My Release. How about My Milvus? Now to sit back and watch the quick installation, and soon we'll see this instance springing to life. Just hang in there. Let's check the logs for the Milvus instance, confirming that everything's just as it should be. And yes, it's pristine and ready. Here's the next leg of our journey. We're going to port forward to this instance and buckle up as we load some data into it. We've chosen the Milvus port 19530 to port forward from our IDE. Now, before we run the code, let's make sure we have a clear roadmap. We'll source some public domain images. From there, we'll harness the power of a TensorFlow library to transform image data into embeddings. These embeddings will be processed in our Python script and stored in Milvus, giving us a semantic representation of these images for use in recommendation, search, and similarity systems. All right, let's roll up our sleeves and begin coding. First up, we'll need a few friendly libraries and the Keras API that offers a more palatable way to manage our machine learning models. We will then reach out to our instance using the connections function from the PyMilvus library. Although our mighty Milvus instance is running in Kubernetes, we will be developing locally to start with. Later, we'll expand this local development work into a deployed production-like application. It looks like we have a few warnings, but the connection seems to be functioning adequately. How about we truly put this to the test by arranging a collection of embeddings? The design includes an ID, a simple integer, and our focus, the embedding represented as a vector of float values. By auto-incrementing IDs, we can avoid manual ID numbering. We'll need a Python interpreter to enable ad hoc work and on-the-fly testing. Let's demonstrate this by importing PyMilvus and examining our fresh image collection. All looks good. Next up, adding some data. Get ready for our trusty ResNet 50 model to perform its magic on an array of images. Our model is extracting unique features from each image as a vector embedding. We'll source our examples from Wikimedia Commons. Let's download colorful cityscapes, verdant plant shots, and a stunning castle. Despite the large image file size, we're cleverly resizing as a pre-processing step. All right, looks like we need the pillow library to properly read the images. No problem. Let's bring that in and we're back on track, extracting features successfully. Our vector embeddings are 2048 values with this particular model. The fun part, data loading into Milvus. After that runs, each image embedding is neatly slotted into our collection. All right, let's keep things moving with a fresh new Python script for testing the similarity search. We'll cherry pick a few valuable imports to copy over. Now, let's orchestrate our search. Just like last time, we need a stable and sturdy connection. Then an indexed collection comes into play. Moving forth, we'll process our image and transform it into a vector embedding. Now things get interesting. It's time to put our search into motion. We're setting our search parameters here and bringing into play an L2 distance metric. So we're architecting an approximate nearest neighbor search across our data embeddings and using the L2 distance, which is Euclidean distance. We're going for an efficient, non-brute force comparison of all the embeddings. Let's run this to see the list of closest matches from our database. Oops, we have an error. A quick root cause analysis shows that our precious collection isn't loaded into memory. So let's give it a wake-up call by adding an index and loading explicitly. Aha! Scores of images and their respective distances all orchestrated beautifully with the closest result up front. Bet you it's the same image we found earlier. And indeed it is. Unsurprisingly, the two plant images have a high vector similarity. Now let's uplevel this setup by making it into a proper web application. Specifically, we'll transform this into a Flask application. Sounds challenging? Actually, we'll only need to tweak the code here and there. After fixing up the code to use the PyMilvus hit class, we get an end result of the most similar image ID. When we run this app, we'll have the images show up with their IDs. You'll notice a familiar structure to our Flask app. We're still using collections and our trusty model for embeddings. However, we're adding an index file at the root of our site and creating a form submission endpoint for uploading an image file. When we upload an image file, we're going to process it, do a semantic search as before, unveil the most similar image file name, and serve that treasure from the static images directory. Let's create that directory along with the HTML file, which naturally should reside in a templates directory. Welcome, my friends, to the application's super slick upload interface. Let's proceed to upload our test image and push it. Voila! Here's the closest image in the database. Of course, with the sprinkle of style and a dash of a better user experience, you could dress this app up nicely. We'll defer to you on that though, to avoid this video becoming a CSS tutorial. For real production use cases, we need to also consider deployment. So we'll deploy this Flask app on the Kubernetes cluster alongside Milvus. We just need to tweak the connection details a bit. Minor adjustment complete. Time for the Docker file. We'll also need a requirements file for our Docker build, so let's generate that. While you should typically be mindful of versions, we can keep things laid back and use the latest. We'll also make clever use of a Docker ignore file to ensure we don't accidentally push unneeded files to our Docker image. For the deployment on Kubernetes, the smoothest route forward would be partnering with the artifact registry to store our Docker image. In this Docker repository, we'll see the setup instructions that we need to be able to push to this artifact repository. And we will build with a name like this and use the latest tag. Let's create the deployment. Remember, we're already authenticated with our Kubernetes cluster here, so we'll be ready. Our Flask app is essentially going to look something like this. We just need to specify the image here. And we'll probably just use a single replica. For the service, we're going to use a load balancer service type, which means that we will get a public IP for this application. All right, we've got a public IP here. Let's validate that our pod is running successfully. And indeed it is, the real moment of truth. All right, here's our application. We'll again load in our plant image, and it seems we're getting an error that we need to quickly correct. We need another requirement in the installation, so it's time to further practice our Docker build and push process. Instead of redeploying the pod every time, you can just delete the pod and let it pull the latest code. All right, let's check the logs here to make sure the app is running. That's looking good. Let's try our application out again. This looks like it's working quite well. We're getting our closest match for the uploaded image. We'll provide all of this code for your reuse in the video description, as well as this diagram file. Thank you so much for watching. Leave any questions in the comment section, and please enjoy responsibly.